Hello everyone. In this video, we'll be discussing about the concepts of current, current density, and we'll derive an important equation related to continuity of current. Let us look at the concept of current now, taking the example of the small circuit. If we want a current flow to happen in this circuit, that requires the charges, especially electrons, to flow from one point to another point in the circuit. That requires some energy or work done. That work is done by this external supply. We call here this external supply as the potential source, and this potential source is going to provide the energy required to move the charges from one point to another in the electric field. In general, we can define three types of currents. One is convection current, another is conduction current, and the third one is displacement current. This displacement current is specifically defined only if the fields are time varying in nature, or in terms of current, we can say time varying current or alternating current will be discussed in the form of displacement current. We have the other two types of currents we'll be discussing in this video. The displacement current will be discussed in the subsequent videos. In general, we will be giving the definition of current, current density, and then go for defining convection and conduction currents. In general, current can be defined as the rate of movement of charges through a reference point. It can be defined as coulombs per second, number of coulombs per second, and it is given by the unit of amperes A. We can write the rate of movement of charges as dq by dt, which is the definition of current I. We can also define the vector flux density for this current, that is called as the current density. That current density is indicated by vector J, which is defined as the current per unit cross-sectional area. So if I want to describe this, there is a flow of current. If we consider a cross-sectional area, through this cross-sectional area, how much of current is crossing? That is defined as the current density vector J. We can give this definition as current per unit cross-sectional area. By mathematically, we can give di by ds, where ds is the cross-sectional area and di is the amount of current crossing this cross-sectional area. This is current density magnitude given with the units of ampere per meter square. From this expression, we can write di as current density multiplied with this ds. So current density is a vector quantity and surface is also a vector quantity. Multiplication of these two in the form of dot product gives this magnitude of current, which is a scalar quantity. This is a small amount of current through the small cross-sectional area if the current density is J. If you want to evaluate the total current over this cross-sectional area, we can do integration of J dot ds over this surface. That is given by the expression I can be given as surface integration J dot ds. These are the mathematical representations of current and current density. We can now shift to discuss about the convection current. So when we talk about the convection current, whenever there is a charge which is in movement, constitutes a current called convection current. In this case, there is no requirement of a conducting material to take the charges to flow. So if the charges are moving in free space, like for the example, in case of electron beam generated by the cathode gun. In that case, the cathode gun generates the electron beam, which doesn't require the conducting medium to flow. If the charges are in movement, if we know the velocity of movement of the charges, we can define this current density called convection current density. We will slowly do some small derivation to get the expression for convection current density. Considering here, a volume of charges is moving in the direction x. So let us consider here this volume as del V. That particular del V volume carries the charge density of rho V. Rho V is the volume charge density of this volume. Then the total charges contained in the volume can be given as rho V into del V. If we consider the cross-sectional area is del S and the length of this volume is del L, in moving the charges, if the charges are moved through a distance of del X, then we can write how much of current will be there due to this movement of charges through a distance of del x. So let us try to define the current as per the previous definition. Del I is del Q by del T, that is the rate of movement of charges. Now we can write del Q in terms of this volume charge density and del V. So rho V into del V by del T we can give. This volume del V we can write in terms of the cross-sectional area and the distance through which the charges have been moved. So this del V can be written as del S into del X. This indicates the cross-sectional area and the distance through which the charges move. We can also write this del X by del T. The rate of change of distance we can write as velocity. Rate of change of displacement can be given as velocity. So this del X by del T we are writing as V suffix X because the velocity of the charges is in the direction of X. So we can write del I by del S as rho V into velocity Vx, where this del I by del S is nothing but the magnitude of the current density. Since the current is flowing in the X direction, we can write J component in X direction. So J suffix S can be given as rho V into velocity, which is in the X direction. In general, the vector representation for this can be given as J vector equals rho V into velocity V, where this current is due to the movement of charges constitutes the convection current, and the current density is called convection current density, which is given with the units of ampere per meter square. Also, we can write the unit of volume charge density is coulomb per meter cube, and the velocity V vector has the unit meter per second. Now, let us discuss the next type of current, which is conduction current. When we talk about the conduction current, for conduction current to flow, we need a medium called conductor with a specific value of conductivity. For any conductor, the value of conductivity will be defined. For that particular conductor, if current is flowing through this conductor, that current can be defined as the conduction current, and we are going to derive the expression for conduction current density. So as per the definition, we know current del I by del S gives the current density magnitude. So we can write current I as J multiplied with the cross-sectional area. If I consider this particular cross-sectional area, as S, then current can be given as J into S. Also, we know electric field will be produced. Suppose if I consider this conductor is connected to a supply voltage of V, in that case, this particular end is charged to positive and this particular end is charged to negative, and the flow of current will be from positive to negative potential, and also the electric field direction is from positive to negative potential. This is going to be the direction of electric field. We can write the relation between electric field and potential. We have already discussed electric field vector is negative potential gradient, or if you want to write only the magnitude of electric field can be given as dV by dL. I'm not considering the direction here or sign here. I'm considering the magnitude relation. So we can write electric field can be given as potential over the length. Suppose if the length of this particular conductor is L, then electric field can be given as potential divided by length L. Now with this, we can define the relation between the current density J and this electric field intensity, which you would have already learned. That is, J vector is equal to sigma times E, where this sigma is the conductivity of the material through which the electrons or charges are flowing, which is given in the units of Siemens per meter, or you can also say this as mho per meter. You can write the unit of conductivity as Siemens per meter or mho per meter. Now with this conductivity value, if we know the electric field, then current density through this conductor can be given as sigma into E. This is for metallic conductor. We call this equation as point form of Ohm's law, or the differential equation of Ohm's law. We can get the actual Ohm's law equation from this J equals to sigma E relation. So we will be discussing how to relate this actual Ohm's law. We know Ohm's law is V equals to IR. We are going to get this relation from this point form or microscopic form of Ohm's law. So we have to write the expression for potential and current density. From that, we will be writing the relation between potential and current. So potential difference between 2 points. Suppose if I consider this is the point B and this is the point A. So the potential difference between these 2 points can be given as VAB. By the relation for potential and electric field, we can write it as minus line integration E dot dl. We have discussed this in the previous videos. You can refer those videos where we have defined potential, work done, and potential difference. So minus line integration E dot dl from B to A. That is the potential difference between the points A and B. Now we can write the electric field is common, multiplying this with the integration dl from B to A. So this integration from B to A gives the length. So E vector dot LBA. Negative of E vector dot LBA we will get. Or if I want to write in terms of LAB, so this displacement, if I consider in the opposite direction, this negative sign can be neglected. So E multiplied with length gives potential. We can write V is equal to E multiplied with length. Now we know the relation for current density and current. Current density J can be written as I by surface area. We can also write J equals to sigma E. Now we will be relating these two. That is, J equals to, I will be writing only the magnitude here. So J equals to sigma E, and we can write expression for electric field from here, which is V by L. J equals to sigma V by L. Now we can write this current density in terms of current. So current density J can be written as I by S, which is equals sigma V by L. Now from this relation, we can write V equals to I into, we will be getting L by sigma S. So we will be moving this L to the numerator, sigma and S will come in the denominator. So now when we look at this expression is nothing but the resistance. This is giving the expression for resistance of any conducting material, which is L by sigma S, or we can write it as L into resistivity by S. We know resistivity is inverse of conductivity. So by this, we can write voltage equals to I into R. So this is the macroscopic form of Ohm's law, or the circuit theory form of Ohm's law. So I can give the proper relation here for your understanding. Potential can be given in terms of electric field as E into L, and current density we can write in terms of electric field, and also relating to the current, we will be getting V equals to IR, which is the macroscopic form of Ohm's law, where the resistance of the conducting material is given as length of the material divided by conductivity of the material into cross-sectional area of the material. You know, the resistance is given in the units of ohms. Resistance is given in the units of ohms. So this is the macroscopic form of Ohm's law, which we are obtaining from this microscopic form of Ohm's law. And from this relation, we can get R also. So if we want to find the resistance of the material in terms of fields, if we want to write in terms of fields, electric fields, this relation can be rewritten. So R can be given as V by I. V is minus line integral E dot dl, and I can be written as surface integration J dot ds, where this J can be written as sigma into E from the point form of Ohm's law. So if we know the electric fields alone in a particular region, we can estimate the resistance of that particular material or medium by this relation. And there are few important observations for conductors or the properties of conductors in electrostatic fields. The first property says static electric field inside the conductor is zero. So if I consider a conducting material, in the conducting material, the electric field is zero inside the conducting material. Usually the electric field will be perpendicular to the surface of the conductors. So usually electric field will be perpendicular to the surface of the conducting material. That is because the charges are present only on the surface of the conductor. That is the second point which is given. The static electric field intensity at the surface of the conductor is everywhere directed normal to the surface. Because for a conducting material, you have all electrons. Because of electron-electron repulsion, all the charges will be deposited on the surface of the conductor. Because of that, only surface charge density exists. Thereby, electric field inside the conductor is zero. Electric field will be directed perpendicular from the surface of the conductor everywhere. So that is the second point. Electric field intensity at the surface of the conductor is everywhere directed normal to the surface. And the third point is everywhere the potential value is same. So if we measure the potential at this particular point V1 and another point V2 and another point V3, we can say V1, V2, V3 are all same because the conductor surface is an equipotential surface. So these are few observations or principles which apply to the conductors in electrostatic fields. The first point being electric field inside the conductor is zero because the charges will be deposited only on the surface, not in the entire volume of the conductor. Second is, since the charges are on the surface of the conductor, electric field intensity is everywhere normal to the surface of the conductor. Then everywhere on the surface of the conductor, the potential is same. We can call the conductor surface is an equipotential surface. Next, we'll be looking at an important derivation, that is equation of continuity of current. We are going to derive that. Considering a region or a volume where current is flowing outside this volume, means charges will be moving from the volume. So the charges, let us say, present inside the volume is Qi. If current flow occurs, this charge Qi has to reduce from inside. Thereby, the electrons or the particular charges will start moving. So if there is a flow of charges from inside to outside, then only you can say the current is present. If I consider Qi is a positive charge, then the conventional current direction is the same as the movement of the positive charge. In that case, Qi, if it is moving from inside to outside, current flow is also going from inside to outside. If Qi, suppose if there are 10 coulomb of charges, if one after the other coulomb of charge means one after the other, the 10 coulomb of charges are moving out, then the charge concentration inside will start to reduce. So we can write this current in terms of charge concentration inside as rate of decrease of Qi. Why I'm mentioning rate of decrease is when the current is set to flow, thereby the charges concentration inside the volume will reduce if it starts to flow outside. That indicates this negative sign. Rate of decrease of charge concentration inside is given by this current I. Now we are going to write this current in terms of current density and this charge in terms of charge density. We know this is a volume of charge, so we can write the charge density for this current Qi as volume charge density. We know Qi can be written as volume integration of rho v dv over this entire volume. And similarly, this current can be given in terms of current density. We know the relation between current density and current, which is I can be written as surface integration J dot ds. So in terms of the current density for the left-hand side and in terms of charge density for the right-hand side, if we substitute, we will be arriving at the equation of continuity of current. So now let us substitute this Qi, which is volume integration rho v dv, into this expression for the right-hand side. So we will be getting minus d by dt of volume integration of rho v dv. Now this time change, that is d by dt, should be applying to rho v or dv. So dv indicates the volume. This volume is a fixed volume. This volume is not going to change with respect to time, but the charge concentration rho v is going to change with respect to time. So what we have to apply is this time differentiation is applicable only for this rho v, since volume does not change with respect to time. So this d by dt is applicable only for this rho v, and we are writing this as partial differentiation because The volume charge density is a function of XYZ and also time. When we consider the current flow, this charge concentration will change with respect to time, thereby the current is produced. So rho V is a function of XYZ and also time t. So the differentiation is only with respect to the time parameter. We are differentiating this rho V partially with respect to time. So current I can be given as minus volume integration dou rho V by dou t of dV. So this is the expression for the right hand side in terms of charge density. Now we have to write this left hand side in terms of current density. We know the relation for current and current density, that is surface integration J dot ds. But here we have to be more specific about this region is formed by a closed surface. Closed surface always encloses a volume. Thereby, this integration for the surface should be closed surface integration. Now, for the left-hand side, we can replace this expression. Thereby, the left-hand side, which is current, becomes closed surface integration J dot ds, and the right-hand side is minus volume integration of dou rho V by dou t. Now, we have to equate these two, but one is closed surface integration, another is volume integration. If we are able to write the two in the similar form, then we can equate the integrands to get the proper equation of continuity of current. So we have to write this left-hand side in terms of volume integration. We can make use of the divergence theorem. We have already discussed the Gauss divergence theorem. Gauss divergence theorem talks about closed surface integration of a vector equals to volume integration of divergence of that vector. In this case, if we consider this left-hand side is for closed surface integration of current density vector, then that can be written by using this divergence theorem as volume integration divergence of current density vector. Now, if we write this left-hand side in terms of volume integration, right-hand side is already in terms of volume integration, we can equate these two integrands. This integrand del dot j can be equated to minus dou rho V by dou t. That is going to be called the continuity equation of current, which is del dot j vector is minus dou rho V by dou t. So this is one of the important equations which talks about the continuity of current flow in the differential equation form. Next, another more important thing which is talking about the energy density in electrostatic fields. If we talk about the energy storage in electrostatic fields, we can take the example of two parallel plates or the parallel plate capacitor in this case. If the two parallel plates are separated by an insulating material, or we can call it as a dielectric material, if these two plates are connected to a supply voltage of V, one plate is going to be charged to positive, another plate is going to be charged to negative. So the direction of electric field will be always from the positively charged plate to the negatively charged plate. This indicates the direction of electric field. If the capacitance of this capacitor is defined, that is usually the ratio of charge stored in either of the plates divided by the potential applied. So capacitance is Q by V, and how much of energy is stored in this capacitor plate, that can be estimated as half into CV square. So this is the general expression for energy stored in the capacitor, which you have learned earlier, where this C is the capacitance value and V is the potential. Now, if we are writing this in terms of charge and potential, so we can write energy stored in the electric field. So this suffix E, W is the energy or work done, and E, suffix E indicates for electrostatic fields. So we can write 1 by 2. This capacitance can be written as Q by V into V square, which gives half into Q into V. So this is the expression for energy stored in terms of charge and the potential. Now we can write, if there are n number of charges present, so we can write this electrostatic energy storage can be written as summation of Qk Vk, where k takes the value from 1 to n. So this is the overall summation in terms of charge and potential. In terms of field values, suppose if we want to write the expression for energy stored in terms of the electric field or electric flux density, that is given by this expression, which is energy stored is half into volume integration d dot E dV. We know energy is indicated in the units of joules. So this is the expression for energy stored in terms of field quantities, and this is the expression for energy stored in terms of charge and potential. Next concept, we are going to define energy density, means how much of energy is stored per unit volume. So per unit volume, how much of energy will be stored can be estimated from this expression. Taking this energy differentiation with respect to the volume will give dWe by dV, that is the left hand side. In the right hand side, if you differentiate with respect to volume, this volume integration will be cancelled. You'll be getting half d dot E. So that is the energy density, which is energy stored per unit volume, which has the unit joule per meter cube. Now, this D and E can be related as D equals to epsilon E. We know if the insulating material or the dielectric material has the dielectric constant epsilon between the two plates of the capacitor, then we can write flux density D as epsilon times E. In that case, this half D dot E can be written as half into epsilon E square. D can be written as epsilon E by using this relation. So epsilon E dot E will be E square. Or if you want to write this entire expression in terms of purely E, so E can be written as D vector by epsilon. So if we replace this E vector as D by epsilon, you'll be getting half D square by epsilon. So these are the expressions for energy stored in the electrostatic field and energy density of the electrostatic fields in terms of electric field intensity or electric flux densities. So with this, I'm concluding this video. Thanks for watching the video.